In this video, I want to talk about the Newton above Hodge theorem. Um, above Hodge. And I'm going to just give an introduction to this theorem. We're interested in this theorem because of this Ax-Katz Chevalley-Warning theorem and the fact that it implies it. So let me just start. So P is going to be a prime number. K is going to be a perfect field of characteristic P. The characteristic of K is going to be equal to P. And we'll think about K being maybe FP bar. The algebraic closure of the field with P elements. R, in this video, is going to be the P-typical width vectors of K. And so in this case, again, R will be ZP, it's isomorphic to ZP unramified completed here. So we have to take the maximal unramified extension of the p-adic integers. This is going to be ZP with just roots of unity whose power is prime to P, so P does not divide the power of the root of unity. And then that's going to not be a finite type extension, so we're going to p-adically complete it again. Okay, so again, if this thing were just FP, then this would just be ZP. Okay. And then Rn is going to be equal to R mod P to the n plus 1. So we're going to use this notation. In particular, R will be something mod P squared. A fact that we have, a fact is that there exists a unique lift of the Frobenius on that acts on R here. And so there's this thing, and so this is an endomorphism of R, so it's a ring endomorphism. So it's a ring homomorphism in particular, and it has the property that for every R in this ring, it's going to be congruent to R to the P mod P. Okay, so this is the lift of Frobenius on this guy, of Frobenius. So this thing exists. Okay, and the theorem that I want to talk about is due to Mazur, and so this is due to Mazur. And it says the following. It says that if x over k is a variety, a smooth variety, over this field k, and it lifts, there's a flat lift to, it lifts to R1, so it lifts mod p squared, then it says the Newton polygon, or all the Newton polygons of x are above the Hodge polygons of x. Okay, so this is, so let me say some things about this. So we're going to have one of these for each I, and this is going to have to do with the ith cohomology. And this thing has to do with eigenvalues of the Frobenius here on cohomology, and this thing has to do with the Hodge numbers. And so what it does is it says that so it says is essentially the multiplicity of the eigenvalues with multiplicity p, right? So we're going to look at, we're going to take an eigenvalue of the Frobenius. And then what we're going to do is we're going to take its order mod p. So it's going to look like p to the n times something. And what this is essentially say is that how divisible it is by something, right? How divisible it is by p is controlled essentially by the Hodge numbers. That's the idea of the theorem, and it'll end up implying this Ax-Katz Chevalley-Warning theorem. And I'm going to link to this video. Okay, so hopefully there's a link now. And okay, so now in order to talk about this theorem, I need to set up some notation and some abstract terminology. I need to talk about crystals and spans and stuff, and that's what I'm going to do now. Okay, so first, let me just give you the abstract definition of an F crystal. Okay, so an F crystal is a pair with a module. So M is going to be an R module, and then there's going to be F is going to be an endomorphism here. So this is an endo of abelian groups, and it's going to satisfy the following property. It's going to be injective, and properties, I should say, and it's going to be semi-linear. So this is semi-linear. So it's injective and it's semi-linear. Again, here, this is this unique lift of the Frobenius on R. Okay, so this is let me make a remark here, is that these form a category. F crystals form a category. I don't know what we should call them. Maybe we should call them maybe F mod, right? F mod R, whose objects are crystals. So the objects are the crystals. And the morphisms, well, if I want to take a morphism of these things, let's call this F. This is just going to be a morphism that's going to be equivariant. So M2, F, and then we say F1, M2, this is F2. Okay, so morphisms will just be maps like this. So these are going to be morphisms. That's what an F crystal is. Also, let's see. So this is just an endomorphism of here. Okay, so what else should I say? So this is going to be free and finite rank. And finite rank. Okay, so that's another thing that I need. Okay, so the primary example that we're going to have is that this is going to come. It's going to be coming from crystalline cohomology. So if X over K is smooth and proper, well, what we can do is we can associate crystalline cohomology. So this is a Weil cohomology theory, and I've done a video on Weil cohomology theories. And so we know a lot of the properties of this thing. Well, it should be a Weil cohomology theory. Let me put it this way. And so that's how you should think of it. You should think of it as kind of de Rham cohomology, but we have this this kind of lifted. So this is going to be an R module, a free finite rank R module. Modulo torsion, it's going to be free and finite rank. And so it always is going to have a Frobenius. May have some torsion in here, but the fact is that phi is going to be injective modulo torsion. Torsion. So it's not necessarily that this is going to be an F crystal, but these guys, HI crystalline cohomology of X over K, modulo torsion, and then the induced map of Frobenius. So I'm just going to denote it by the same thing. This is going to be a crystal here. Okay, so this is the primary example coming from crystalline cohomology after you mod out by torsion here. So that's what that says, TORS, torsion. Okay. So we talked about what a F crystal is. Now I need to define what a span is. So I'm going to give you this abstract notion of a span. So definition. A span, and so this is, I think this definition is due to Maser, is a morphism T of M1 to M2, where, so this is going to be injective. M1 and M2, the rank of M1 is going to be the rank of M2. Here M1 and M2 are modules in here, and they're going to be of free and finite rank. Okay, so they're just going to be like a direct sum of copies of R, isomorphic to a direct sum of copies of R. And so this is, yeah, this is an injective morphism of free modules of finite rank. So you may think this is like stupid, right? So this is a discrete valuation ring, and we're just looking at things with the same rank and injective maps between them. So it seems like this almost carries no information, but let me give you an example here. So the example to think about it is maybe you can take ZP and you can take ZP here, and you can take T here, and then the lift of the Frobenius on this is the identity map. So we don't really need to worry about equivariance here, but this is just P times X. So the idea is that these spans capture information about divisibility by P. By P. Okay. So this is what a span is. So let me say something else. So let me make another remark. Is that spans form a category. Span R is a category. So the objects, well, these are going to be maps. Let's say M prime to M, which are spans in the sense of this definition. So they're modules, R modules, free finite rank, and then this map is going to be injective. And morphisms, well, morphisms are going to be M1 to M1 prime to M1, T1. So they're going to look like this. F, let's say prime, M2 prime, M2, let's call this F. So the morphisms are going to be these pairs of F primes and Fs, where we have this diagram that's going to commute. Okay, so this is going to form a category. This category has tensor products and wedge products, and all these constructions like this. Like this. Okay. In fact, okay, so I said that spans are going to capture information about divisibility by P. Let me say something more about this. So let me give you kind of a fact. So suppose M prime, this thing here is a span, and R span. Okay. So it's an element of this category SPNR that I made. Okay, then well, there exists a direct sum decomposition of this thing. Then there's this fact that there exists a direct sum decomposition of the target here into pieces from I is equal to 0 up to infinity. So maybe some of these will be zero-dimensional pieces. So there's this kind of direct sum decomposition where the image of this guy, the image of T, or the image of M prime into this thing, so this map's injective, is going to be the direct sum from I is equal to 0 up to infinity of P to the I mi. So these are so you can direct sum. You can decompose it into pieces where the image is going to be more. Well, you multiply each of these pieces by a certain power of P, and then they become, you know, it is what it is, right? So back in this case here, we just have one single piece. So M1 would be just the whole thing, and then the other ones would just be 0. Okay. Because of this, we can define this notion of an abstract Hodge number. So now let me give a definition. So this gives rise to the abstract Hodge number. In this decomposition above, So we say that EI of T, so this is the abstract Hodge number of the crystal. Hodge number of the crystal. This is going to be equal to the rank of this piece here, Mi. Okay, so this is what we have. So this is the definition of this abstract Hodge numbers of the crystal, or something like bizarro Hodge numbers. Okay, so they're just kind of like, so you shouldn't think about too much about this being the Hodge numbers. I guess if you do want to think about this, okay, like in terms of Hodge numbers, so what you should think is that M is going to be something like Hj, maybe de Rham cohomology. This is how you should think about it. And then EI is, let's say, I j minus I. Okay, or little h. Okay, so they're the things that add up to the ith part. Okay, so they're kind of going along here. So this is what you should think about. Okay, so but this is generically something like this will be true. Okay, so that being said, let me just say some. Let me give you some important fact. An important fact. So an important fact is that given a span, so the first, so one can compute, so compute EI of these wedge powers of, let's say EJ of these wedge powers of T in terms of in terms of E, let's say J of T's. Okay, so you can if you have these wedge powers, you can compute the Hodge numbers, the abstract Hodge numbers of this crystal, of the wedge powers of a crystal, in terms of the normal Hodge numbers of the crystal, the Hodge numbers of this crystal. And the first non-zero, it turns out that this is important. The first non-zero Hodge number of this jth power of an ith power of here is the following number. It's going to be E1. So this is, I'm just going to write down something messy, and it turns out that j minus 1, ej minus 1. This will maybe become clearer in a second. 0 ej minus 1 here, where here we have I is going to be the number that's in E0. So this is kind of a crazy expression that I'm writing down. I realize that now that I was trying to avoid writing down crazy expressions in writing this, because this business has quite a few crazy expressions. But this is one of them. So here, these EIs here, these EIs are going to be the Hodge numbers here of this one here. And so the fact that I wanted to tell you is that you can compute the first Hodge number, the index of the index of the first non-zero Hodge number. So this is the index of first non-zero Hodge number. Okay, so this would kind of be like the Hodge level that we had talked about previously. If you're familiar with this, maybe I'll make a link here. Okay, so then let me just kind of explain a little bit more about this, and so that we can get some familiarity with Hodge numbers. Okay, or with these abstract Hodge numbers, and maybe so this will become a little bit more believable. So first. first, let me say something. So let's recall some facts about wedge products. So recall that if I want to take the nth wedge power of a V1 tensor up to V, let's say M free R modules, this is actually going to be the direct sum, and then we have I, let's do this V0, I0 up to IM. This is going to be equal to n. So you just kind of do like an expansion of these things, and then we have this. We have this tensor powers here. I0 wedge of IM VM. Okay, so we can do this, and so we also have that if we have, so here's another thing, is that given, so this is one fact. Another fact is that if we're given a morphism here from two free R modules, then this induces a map, right? So into the nth wedge power of V, and then we have this nth wedge power of T into the nth wedge power of W. And what it does is it takes T. What it does is it takes V1 and it takes all these wedge powers here, Vn of these guys, and it maps it to. So this is wedge n T of this thing. Well, what it does is it takes each one of these guys and it wedges all them together like so. Okay, so this is how you define this map here. Okay, so what I'm saying here, what these facts are going to be used for is to talk about this statement that I said about this wedge power of a crystal. Okay. So in particular, what I want to do is I want to look at this in a special context. So again, we had this direct sum decomposition of the image. So if T from, let's say, M prime to M was a crystal, we had that the image of T looked like this direct sum of these MIs here, from I is equal to 0 up to infinity, let's say. Well, we don't really need to take infinity because this is finite rank, but we'll say some, well, we can fix this to some small number, but I'll just leave the infinity there for now. And so what I want to do is I want to look at this formula here, and this kind of thing here in this context. So what does this mean? So here, if we're going to take Vj to be equal to, in this formula here, or here, Vj to be equal to p to the j mj, what does this tell us? Well, then we have that the wedge power of the image, so the image of, let's say, the nth wedge power, or the, I don't know, let's say the why not? Why don't we say nth or mth wedge power of I don't know, which we do. Let's do nth. Okay, the nth wedge power of M, or let's say of T, sorry. So this is going to be some big direct sum of I0 up to IM, and then we're going to have a big power here of I1 plus 2 I2 plus M IM, or N IN, and then we're going to have these things here of M0. And then we have this thing all the way up to IN. Let's see, how many do we have? So, we do need to fix one now. So let's take this to be capital N. IN of M N, like so. Okay, so we're going to have this big direct sum of things like this, and now these pieces are going to come out, and now you can kind of see, like, how this kind of crazy combinatorial description of the Hodge numbers are going to come out. So what we need to do is we need to essentially find so we need to find all these things that are going to be the same and clump them together, and then compute the overall dimension of the direct sum of these things. So we'll actually have to change the direct sum to be, so we'll actually have to write something like this to be the direct sum of p to the a, and then we're going to have some big vector space here that's going to, or module here that's going to be v sub a. And what we need to compute is we need to compute the dimension of v sub a to compute these Hodge numbers. So this is, we need to compute these. To compute dimension of these. This is messy. Okay. So instead of just doing that, I kind of want to do maybe an example so that you can kind of see what's going on. So here's what we're going to do. So let's do kind of an example of how this works. So let's suppose that this image of t looks like p to the a with some module here, and then p to the b and some module here, let's say w. Okay. So in this case, we could even make it more concrete. Okay, we could say that a is equal to 1, so this is just pv, and then we could have b is equal to 2, so this could be p squared w, like so. And then what else could we have? So in this case, the Hodge numbers, E0 would be 0, since there's 0 piece. E1 would be equal to, well, this would be the dimension of V, and let's call this N. And then E2 could be the dimension of W, which would be M. Okay. And suppose we wanted to take the second wedge power. Okay, we take the second wedge power. If we take the second wedge power of this thing, then this is going to be, well, p to the AV with this thing p to the BW. This is going to be decomposes into a bunch of things. So this becomes the second wedge power of this thing. And then the first wedge power, or the 0th wedge power of this thing. Direct sum the first wedge power of both of these things, and so the 0 p to the a v, this thing, second. Okay, so we have this. What does this become? So this becomes just equal to the second wedge power, direct sum, so this just becomes p to the AV, p to the BW, direct sum, and then we have this thing, p to the BW, like so. Okay, and now this comes out, this is p to the 2b, or p to the 2a, lambda squared v, direct sum. This is p to the a plus b, v tensor w, and this is the direct sum of p to the 2b, lambda squared w, like so. Okay, and if we go back to these numbers that we picked, so let's go back to the numbers that we picked. So a was equal to 1 and b was equal to 2. If we do that, so what does this become? So this becomes p to the, a was equal to 1, so this is 2, so this is p2, second wedge power of v, and then this is 2 plus 1, which is 3, okay, and then this is 2 times 2, so this is p to the 4th, lambda squared w. Okay. And let's look at what this has now. So now, so this tells us that E0 of the first wedge power of, or sorry, the second wedge power of this map of something where the image of t was like so. So this is 0, right? E1. So this is equal to 0. E2. So this is equal to, so E2. So this is the dimension of V. So this is n times n minus 1 divided by 2, since it's the antisymmetric part. E3 of this thing. So this is these two things multiplied times each other, m times m. And then E4 of this thing. So this is m times m minus 1 divided by 2. Okay, so now we've computed these numbers, and we want to compare this to the crazy formula here, this crazy formula. Okay, and so what it's going to tell us? It's going to tell us the index of the first non-zero Hodge number of this thing. So the index of the first non-zero Hodge number, so let's look at this. So we need to find where I is going to be in this interval. Okay, so this was 0. So let's look at where I is in. We need to find the j so that I is in here. Okay, so let's look at that. Okay, so I is 2, and it turns out that 2 is going to be an element of, well, so we had 0, then E0 was 1, so we had 0, E0. So this is going to be E0 to E0 plus E1. So this is equal to, let's just say that, so this is E1. So let's see, what do we have? E1 was n. So this is 0 to n. Okay, so we'll just suppose for now that n is bigger than or equal to 2, so that this makes sense. Okay, if n is bigger than or equal to 2, then then in this formula here, let's go back to the formula. Here, if this is this, then so then j is equal to 2. So j is equal to, I believe, 2. So this means that, j is equal to 1 even. J is equal to 1. So in the formula, j is equal to 1. Okay, and so when j is equal to 1, this thing collapses. So this thing just becomes this when j is equal to 1. So this is 0. Okay, so the formula predicts first non-zero Hodge number, Hodge. So this is again, these weird crystalline Hodge number to be, well, so let me write it down again. 2e2 plus j minus 1 ej minus 1 plus j times I e0 plus ej minus 1 here. So okay, we had I being 2 because we took the second wedge power, right? So this becomes 2. This thing goes away. So this is this part here is 0, right? Plus, then we had j being 1, and then we had 2 minus, and then here we go all the way up to j minus 1. Again, j was 1, this was 0, so this is 0, so this is 2. And let's go back to what we computed before. Okay, here. And we can see that here this is indeed the index of the first non-zero Hodge number. So this is the first Hodge number. Okay, so this is useful. So this is kind of useful for us. This formula here. So this is the important fact that we're going to need. Okay, so that being said, I'm going to just kind of continue with the rest of this. Maybe I can chop the video here